Okay.
So we had one example from last time, we'll get through that. And the rest of the time will be devoted to conceptual stuff. Just some ideas that I want you guys to understand as we move forward. So not much computation left over after that. So let's actually just jump into it. So a problem like this, similar to this, was on the quiz, but find f prime by definition. What is the definition of f prime? That was on the quiz, but you have to just remember what that is. F prime of x, how is it defined? Yeah?
F plus h plus f, minus f. Are you asking the right thing? Am I answering the right thing?
No, not exactly.
Why? Oh, well, the limit. Sorry. As h equals 0.
Right.
Sorry.
So that is how we define the derivative. Without the limit, it's a difference quotient. It's the slope of a secant line. With the limit, it is the slope of the tangent line, and we call that the derivative. Yeah, so let's apply that to the radical function. What would f of x plus h look like?
Square root of x plus h.
And f of x is square root of x all over h. How do I take that limit? Because I can't plug in h equals 0. What can I do? Yeah?
Do I conjugate?
Conjugate, rationalize. What's the conjugate?
Square root of x plus h plus square root of x.
Right, you multiply and divide by the conjugate. In the top, that's the difference of squares, because it's like a minus b times a plus b, so you get a squared minus b squared. In the denominator, you just multiply across, and once again, I have to warn students about this, because they have the knee-jerk reaction, never expand the denominator. You can't simplify a fraction by expanding the denominator. So you want to keep that in factored form, don't multiply that out. Other than that, you'll notice that the x's would cancel and kill each other, and we would have the limit as h approaches 0, h over h times. Now the h's cancel. And what's that going to be as h approaches 0? Yeah?
1 over 2 root x.
1 over 2 root x. And now that is another rule that we can know. We now know that the derivative, remember this notation, you're at d dx, it's Leibniz notation, of radical x is 1 over 2 radical x. This is something that we know now. The derivative of radical x is 1 over 2 radical x. To differentiate the square root, get 1 over 2 times the square root. This, and remember this is the derivative parenthetical statement with respect to x of radical x. That's how you read this, the derivative with respect to x of this function. So with respect to x, this means x is your independent variable. It's the input. It's the guy that you're manipulating and seeing what happens to the function. So yeah, got that. Now I want to just talk about some ideas. Right? So the ideas are going to be important here, just as they are in a regular calc class. Even though it's applied calc, concepts are going to be important because you need to know that you're in the right situation so you can apply the math that you know how to apply. So let's look at some consequences. So there are interpretations of the sign of the derivative. Now, when it comes to slopes, right? Let's say you're in a situation where you're doing like, you have a line going like that versus you have a line going horizontally versus your line going like that versus the vertical line. Tell me about the slope n of here in terms of its sign. Is it going to be positive or negative?
Positive.
Right, so here m is positive. Here, horizontal line? No. Is 0, right? And 0 is not positive. 0 is not negative. Positive is defined as strictly greater than 0. Negative is defined as strictly less than 0. Here, you have m is less than 0. Here, you have m undefined. What I do want you to take away from that is remember slope is another name for derivative. So in fact here we could say the derivative is greater than 0. Here we can say the derivative is 0. Here we can say the derivative is less than 0. Here we can say the derivative is undefined. We'll talk about more places where the derivative is undefined as well, but vertical things, derivatives don't like being vertical. Now, what I also want you to take from this is the certain behaviors of the function. How can I interpret the fact that the derivative is going to be greater than 0? In general, what I can say, whenever your derivative is greater than 0, meaning you're moving in this fashion, as you move from left to right, you're going up, we call that behavior increasing. Whenever here, when you're moving down as you go from left to right, we call that behavior decreasing. This you can't really say anything about it, it's undefined. This is either called non-increasing or non-decreasing, depending on what context you want to talk about it in. Right? But that kind of leads to an important fact of an important interpretation. Whenever your derivative is positive, that means so this leads to an important general fact, right? So it doesn't just apply to straight lines, right? So you could have a function that's doing like this, and if you measure a tangent line at some point, you'll notice that the tangent lines are always pointing up, just like a straight line is. So you can talk about your derivative, so this is your function. You can talk about your derivative f prime as being positive here, right? And that kind of tells you about the behavior of the function that you're looking at. And the function itself, like I said, is not the important thing, it's what it represents. But, so you can apply this in general. We say f of x is increasing if the derivative is greater than 0. And we say f of x is decreasing if the derivative is less than 0. Right? So that's the answer to the bonus. Whereas define what it means to be increasing in terms of an inequality. That's going to be your inequality. Whenever your derivative is positive, it means you're increasing, you're moving up as you go from left to right. Whenever your derivative is negative, it means decreasing, you're going down as you move from left to right. Very important idea. very basic, very simple as a one-off factoid, but it's actually super important when you start to fully talk about the consequences of increasing and decreasing and what information you can gather from knowing a function is increasing or decreasing. You'll be surprised how much use we'll get out of that fact. What else do I want to talk about? Higher derivatives. Often, it will be the case that after taking derivative, we will be able to do it again. And again. Okay. So this is the idea of taking finding what we call higher derivatives. So you can have a function, you can take a derivative of that function, you'll get another answer. And what you can do is you can take the derivative of the answer and get another function, and so on and so forth. You can keep taking derivatives. So, for example, we've proven that if you take the derivative of x squared, you get 2x, and 2x is just another function. You could actually take the derivative of that. And we've also proven that if you were to take the derivative of 2x, the answer would be 2. That's a constant, and we know how to take the derivative of that. Take the derivative of 2, you get 0. That's another constant. Take the derivative of that, you get 0. And you just can keep taking derivatives, right? These guys are called higher derivatives. And let's talk about notation for higher derivatives. There's the Newton's prime notation and the Leibniz notation. And then you can talk about the derivative that you're talking about. So, you can have a function. Here you can have y. Here you call this the 0th derivative. Right, so the original function you can think of as the 0th derivative. Then you can take the first derivative, f prime, which we've been talking about. Right? Now that guy, in Leibniz notation, is dy dx, and this guy is the first derivative. Now, how do you actually go higher? How do you explain that you're going higher? In notation, what Newton does is he puts another notch. So you put 2 notches. And basically what that means is you took a derivative, and then from the result, you take another one. You took a second derivative in fact. Right? How that looks on the Leibniz version, it's d squared dx squared. It's like you multiply this by another d dx, right? So this is, y was your function, you multiply by d dx, similar to the notation that we had before, that's the derivative. Multiply again by d over dx, you get d squared over dx squared of y. That is another derivative, that's the second derivative. You can keep going. You can do the third derivative, the fourth derivative. Now these might not always exist, except in applied calculus. Every time I ask you a function, we'll always be able to do this. But in general, it's not something that you can always do. There are functions that you can differentiate once and only once. It won't actually work another time. But many times it'll actually work out. And you can keep going. Eventually, writing a bunch of notches is just going to get like really annoying. Like, what about we want to talk about the 15th derivative? Who's going to count off 15 notches? Eventually, when the numbers get higher, usually higher than 4, we instead put a power in a parenthesis. So it's written like a power, but there are parentheses around it, and that's the nth derivative. And this one would, of course, look like dny over dx to the n. That would be the nth derivative, right? So, for example, I can say f17 of x. This is the 17th derivative. So, oftentimes you'll be able to take derivatives over and over and over again. These are called higher derivatives. Now, one of these is particularly important for us. the second derivative. First derivative also. And of course, the original function is going to be important for different reasons. We're not really going to have much use for the third derivatives or higher, but the 0th, first, and second derivative, we're going to be applying those in many ways. One way to apply the first derivative is to talk about increasing or decreasing. Something is getting bigger or smaller over time. We can apply the first derivative to that idea. Right? We can describe getting bigger or smaller in terms of the value or the sign of the first derivative. So that's important. So for the moment, let's talk about the second derivative. This has many applications. Some common ones. Well, one is to motion. So like in physics sense, so if you define a function, s of t, called a position function, right? Here's a function that's tracking your position at some time. So t is time, you plug it into the function s outputs the current location. It turns out that if you were to differentiate, find the first derivative of this, you obtain what's called v of t, the velocity function. Now, velocity is like speed in a particular direction. We'll actually do some examples of that pretty soon, but just so you know about this thing existed. And it turns out that you can actually take a derivative again in general. And that also gives you a useful function. This gives you a function called the acceleration function. Now, the acceleration function is a function that tells you how is your speed changing? Are you speeding up or are you slowing down? For example, whenever someone tells you a value for a gravity, for example, so some of you might know, the acceleration due to gravity is 9.81 meters per second squared, negative usually because it's moving down, or 32 feet per second squared in the negative direction if it's moving down. What that means is if you have an object falling to the earth, neglecting air resistance and all that, the gravity of the earth is going to speed that object up at 9.81 meters per second, meaning if the object was moving at 0 and you let it go, 1 second later it will be traveling at 9.8 meters per second. Another second it will be traveling at, double that. A third second it will be traveling at triple that, right? Now there's something called terminal velocity. Eventually it'll speed up to a point where it doesn't speed up anymore, but every second it will add 9.8 to its current speed. So the speed is not going to be the same. It will be falling faster and faster and faster until it actually hits the ground. Acceleration is what tells you about that. Now there's a physics application for the third derivative. It's actually called the jerk function. So if someone calls you a third derivative, it's not flattering. So now you know. You're being such a third derivative now, Becky. Yeah. So they're really...
Shut up.
So third derivative, we won't apply it, but position, velocity, acceleration, we're going to talk about that because it's a very important thing. This is where am I? How fast am I going? Am I speeding up or slowing down? Right? Those are the three questions that these functions can help you answer, and the second derivative comes in handy in answering that question. Another one is what's called concavity. So this is regarding the other bonus problem where I talk about concave up or concave down. So concavity, this is a geometric interpretation. And it's all about shape. So, give some definitions here. Definition. F is said to be concave up if its tangent lines are always below on that interval. So that means f is going to look like this, or f is going to look, that's if it's increasing or decreasing, right? So it'll look like this or that. Basically meaning, if you were to, at any point, plot a tangent line, the tangent line is always underneath the function. It's cradling the function. Plot a tangent line here, your tangent lines are always underneath the function. Whenever your function has this behavior, we say it's concave up. So note here that the slopes of the tangent lines namely f prime is increasing. One thing you'll also recognize about these functions is that whenever you measure the slope gets steeper and steeper and steeper and steeper. The slope is growing. Here it's negative, but it's getting less negative. It's moving on to 0. So that's also increasing. The slope is increasing for concave up functions. And we know increasing means derivative is positive. So this means slope increasing means that the derivative of the slope is positive. But what is the derivative of the slope? This is like taking the derivative and then taking the derivative again, right? This gives you the second derivative is positive. And therefore, you can actually define this kind of shape based on an inequality of the derivative, i.e. f is concave up in a region if its second derivative is positive there. That's like a definition you should know. Similarly, we can talk about a behavior called concave down. If it's concave down, if its tangent lines always above. Notice that if your graph shapes like this, that would be the case. At any given time, I plot a tangent line. Tangent lines will be above our function. This means, notice that the slopes in this case are decreasing. My slopes are getting less and less. They're getting more and more negative. Or it starts out positive, but it's getting less positive. This means slopes is decreasing. And that means f is concave down if f double prime is less than 0. That's what we call it, a double prime. Now, one thing I want you to notice is that this is about shape. It's not about increasing or decreasing. So, if you're looking at concave up versus concave down, you can be concave up and increasing. You can be concave up and decreasing, right? It doesn't have to do with increasing or decreasing. So you can be concave up and increasing. You're going to shape like that. You can be concave up and decreasing. You're going to shape like that. Here you can be concave down and increasing. like that. And you can be concave down and decreasing. In a shape like that. What's important here is your second derivative is positive in both these scenarios, and your second derivative is negative in both of these scenarios. Now, in the first scenario, your first derivative is positive, while over here your first derivative is negative. Over here your first derivative is positive, while over here your first derivative is negative. And I'm going to talk about properties. We're going to combine all this information soon. Another way you can remember concave up is concave up like a cup. And you can think of something as being concave, is it down already? Down like a frown. Concave up like a cup, you're happy, you're smiling, you're feeling positive. Concave down like a frown, you're sad, you're feeling negative. Right? In terms of the second derivative. And it tells us about the shape of the graph. We'll talk about the consequences of that next time. Some ideas, very important ideas for you. We'll stop there. Pick up with that tomorrow.